is an integral part of this semester, because a lot of the processes we're going to see involves oxidation and reduction. Okay, so to start off, we need to learn how to calculate the oxidation numbers or the oxidation states of carbons. Okay, so I have drawn a series of compounds here, and what we are trying to find out, we need to find out what is the oxidation state of the carbons that I have labeled in the red. Okay, in red. So if we think about the first compound, what is the name of this compound?
Ethane.
Ethane. So what is the, how do we calculate the oxidation state of carbons? So we are thinking of doing the one that is on the red. How do we do that on ethane?
Based on what other elements it's attached to, what atoms are attached to it.
All right, so we need to find out, we need to see what other atoms are attached to. So in this case, that carbon is attached to a carbon on the left, okay? And then it is attached to 3 hydrogens, right? So now what?
Carbon should be +2 and hydrogen is +1.
Well, we can't say that. So it is dependent on the context. So the carbon-carbon bond, because it is attached to the same element, okay, this will not contribute anything. So this will be 0. Now hydrogen, between hydrogen and carbon, we know that the hydrogen is always going to be plus, right? So think about the electronegativity Gen Chem. So hydrogen, right? This is +1. This is +1. This is +1. But carbon is attached to the same element carbon. So that carbon-carbon bond has, that doesn't contribute anything. So that will be 0. Because electrons are shared, right, between the 2 elements, which are the same type. So now here, if we have the 3 hydrogens, H's are going to be +1, right? Yes or no?
Yes.
Yeah. So now, to calculate the one on the carbon, we need to first identify if this compound is neutral or it is charged. Right? So the way it is drawn, this compound is neutral. Right? So in order to make the overall oxidation state, like overall charge of the compound to be 0, what must be the oxidation state of the carbon? The one I have drawn on the red.
-3.
-3.
So these 3 hydrogens give you +3, right? So this must be -3. Okay, so that carbon, this carbon must be -3. Right? It will be more clear once we go to the next one. So the next one is what? Number 2. What compound is that?
Ethanol.
Ethanol. So on ethanol, right, again, we have carbon-carbon bond, so that is not going to contribute anything. So here again, we have H as +1, this is +1. Now oxygen is always going to be -2. So oxygen -2, but then there is an H attached to it, so that H is going to be +1, right? So now what will be the net charge on the peripheral substituents on the carbon?
-1.
-1. No, yeah, so the peripheral ones are going to be +1, +1, right? And then -2, +1. So this is going to be +1, the net. So in order to neutralize that, this carbon must be -1, right? Are you following what is going on? Everybody with me?
Yes.
Yeah.
Yeah.
So then what did we do going from ethane to ethanol?
an additional oxygen.
No, think about the oxidation or reduction. What happened here?
It was
Reduced.
oxidized because the charge is higher.
Right? So it's oxidized by how many electrons?
Two.
Sorry?
Two.
2. So we lost 2 electrons, right? Going from ethane to ethanol. Now, what about the next one?
It's an aldehyde.
It's an aldehyde. I think to avoid confusion, I should make these a different color and just leave the carbon in red. So this is going to be black. Okay. All right. So it's an aldehyde. It's and then so how do we calculate the charges on the aldehyde? So this is still +1, oxygen -2, right? So I have net -1 here. Then that means my carbon must be +1, right? Still, it's a neutral compound. Make sense?
Yeah.
So now here we got then carbon is +1. Again, it's a 2-electron oxidation. Keep going down. Next one. So how do we do the next one? It's an acetate, right? It's an acid. It's a carboxylic acid. So how do you do this?
It's attached to 2 oxygens for a total of -4. And then the 1 hydrogen is a +1.
Okay.
So it should be that the carbon is +3 to neutralize it.
All right. So now here it's +3. So again, we remove 2 electrons, right? Okay. So now I think I haven't drawn one. So let's just do 4 prime. Actually, let's just erase this and draw CO2 here. So let's see what happens here. So now I have drawn it as carboxylate. So how do you get this?
-2 on the oxygens.
So oxygens are still, right? So now how much the carbon should be?
+3. So you still have the negative.
All right. So it still has to be +3, right? Because see here I have a net charge negative. Okay, this is my negative charge. I have a net negative charge. So I have to balance the charge. So and that I can do if the carbon is +3, and it makes sense because still we are looking at carboxylic acid, right? It is just protonated versus deprotonated form. So the net charge, net oxidation state of that carbon is not going to change because it is the same functional group. Make sense?
Yes.
Yeah, everybody with me? So we got net -4, but then I have an overall charge is -1. So then to make that happen, that carbon must be +3. Okay, and then the last one was our CO2. So CO2 is the most oxidized carbon that you can have, because carbon can have +4 max, right? So -2, -2, and then this must be +4. So the point of doing all of that is that the food is oxidized, and it is giving up electrons. So you can see that the food we eat, fat or whatever sugar, when it goes to CO2, the carbon is already in the highest oxidation state possible, right? Make sense?
Yeah.
So that's why it's an oxidation process. All good here?
Yes.
Okay, all right, good to know. So now we need to look at any confusion, any question?
I'm
Make
confused
sure.
on number 5.
Number 5.
Mhm. Could you go over that one, please?
So number 5, we have still we are looking at this oxygen. So this oxygen is -2, and that oxygen is still -2, right? So my overall charge is -4, the ones that are attached to the carbon. But the carbon cannot be +4. So if I make it +4, then let's make it +4 for the sake of it. Okay. Then it will be a neutral, right? So +4 -4 going to be 0. But look, my charge is not 0. My charge is negative. I have a negative charge here, right? So to make that negative, this +4 must be +3, so that I have a net -1, right?
Okay.
Got it?
Yes, thank you.
All right, okay. So now moving on, so we're going to talk about NAD plus. So we'll talk about NAD plus going to NADH. And the way it happens is that, so first, let's see, is it an oxidation process or reduction process when you go from NAD plus to NADH?
Reduction.
Reduction.
Okay, so yeah, so this is a 2 electron reduction. Okay, so we need to give 2 electrons. So once we do that, then going from NAD plus to NADH, we are reducing NAD plus. Okay, in the process, we also need a proton. Okay, so the way to think about the NAD plus as a coenzyme in biological processes is that, so H plus, and then I'm going to combine these 2 electrons as 1 electron plus 1 electron, right? So when you have H plus plus electron, then you're going to get H, right? Neutral H dot, right? Plus minus is going to be 0, H dot. Then we add another electron, right? So from H dot, when we add 1 electron, then we get H minus. What is that H minus called?
Hydride.
So this is a hydride. Okay. So when you have H plus and 2 electron, you think of that as H minus. Okay. So that H minus is what gets attached to the NAD plus to make NADH. And that is why NAD plus or NADH is always, so always they will do 2 electrons, they'll involve 2 electrons. So this is a 2 electron. If it is NAD plus, it's going to be acceptor. Okay, if you're going from NADH to NAD plus, then it will be donor. If you look at the structure, it will become more clear. So in the slides or in the book, you will find the structure of NADH and NAD plus. So if you look at that, it has this kind of structure, and then there's a nitrogen here, and this nitrogen is attached to a big functional group R, and it has a double bond here, here, and the nitrogen is plus. So this is our NAD plus. I got an H here. Okay, so this is NAD plus. what happens when the H minus comes, the hydride we just looked at, this is going to act as nucleophile, okay, organic chemistry. And it is going to act as nucleophile, it's going to attach there. Let's make that red. And we're going to push arrows. So this double bond is going to shift here and this is going to become neutral. So the compound you're going to get from here is going to look something like this. Okay, so now remember, notice that this charge is neutralized because of the electron pushing. So we have double bond here, and still R is there. This doesn't change. Now we have this H, and we also have another H. Right, this is the hydride that came. That red H that's the hydride that came. Make sense? Do you see the structure? This is NAD plus, this is NADH. So remember, NAD and NADH and NAD plus always involves 2 electron. It's a 2 electron process, always. Yeah, so I wrote that here, up there, always 2 electron process. And it is a hydride acceptor because of that. So, if it is H, then it will be 1 electron, but because it's hydride, it is 2 electron. So where is this H coming from, this hydride? Where is it coming from, you think?
Proton pumps.
So this is coming from substrate. Okay, substrate. So let's look at an example here. Let's do lactate. Anyone knows the structure of lactate? So tell me the structure of pyruvate, then I'll help you how to know the structure of lactate. How do I draw pyruvate? How do I write pyruvate?
H3C, single bonded to a carbon atom, which is therefore bonded, double bonded to oxygen and single bonded to hydroxide.
So this is going to be pyruvate, right? And then lactate is the reduced form of pyruvate. Okay, so we're going to reduce that ketone to alcohol. So the structure then, therefore, of lactate okay, so this is lactate. This is a reversible process. What is the oxidation state of the carbon in red? Let's do that first. So the one on the left, what is the oxidation state of that carbon on the left?
Be 0.
All right, so how did you get to 0?
The hydrogen off of the carbon by itself, and then the hydrogen on the hydroxyl group is +1, and then the oxygen is -2.
So this is +1, this is -2, this is +1, right? So we got -2 +1 +1, 0. So that carbon right here must be 0. And then what about the one on the right?
+3.
How did you get +3?
Both the oxygens are -2, but since there's still a negative charge on that one oxygen, the carbon will only be +3.
Yes, but we are not counting charge because we are looking at the one that is central carbon, not the one on the terminal. So this is just -2, and this will just be +2. Because remember, this part didn't change. This part is the same. And we're not considering that carbon, the carboxylate carbon. We're considering the central carbon. So how many electrons did it gain or lose?
2. Lost 2.
Lost 2. So it lost 2 electrons. So it lost 2 electrons. Okay. Now, this is dependent on NADH or NAD plus. So going from lactate to pyruvate, which pair do I need? Do I need NAD plus or do I need NADH?
From left to right, you
Yeah.
need NAD plus because it can accept the electrons.
All right. So we need NAD plus because it is an oxidizing agent, right? It is used to oxidize. So we need NAD plus. Similarly, going from right to left, we need NADH because we will be reducing pyruvate to lactate. What else did we lose from left to right?
2 hydrogens.
Okay, so we lost 2 protons, right? We lost 2 protons. So then the way to think about protons is that this is not a balanced reaction, by the way. Okay, I just drew it here. I should draw it as plus. There's a proton coming, and we're going to see in a second how that reaction actually happens. So again, when we think about 2 electron and 2 protons, okay, so think about breaking it up. So we have 2 electrons plus 1 proton plus 1 proton. So 2 electron plus 1 proton is the same as we just did above, right? See here, we already did here. 2 electron plus 1 proton is equivalent to what?
A hydride.
Hydride. So this is equivalent to an H minus. And then H plus, the other proton, is it remains as a proton and it is lost to the solvent. Okay, so that proton is what is lost to the solvent. The way this reaction happens is that I should color code. I just don't want to confuse you guys, so just make sure I color code it. All right, so there you go. Okay, so the H that is attached to the carbon directly is the one that is lost as hydride to the NAD plus, right? So you see that the red H, where it is going to the NAD plus, okay, to NADH. Same here, that's the red hydrogen that is making the hydride. But the black H that is attached to the oxygen, that is the one that is released as proton to the solvent. Do you see what I'm trying to say? So I just very briefly, okay, the way this happens is that kind of running out of space, so I'll do it here. So something like this would happen. So we got that is going to be pushed and this bond is going to release. So that's why H is released as hydride. It is taking both the electrons. Okay, and that's how you're getting to the pyruvate and NADH. So again, color code the H. All right. So again, to think about NAD plus NADH is always a 2 electron acceptor or donor, depending on what you're looking at, and it will have a hydride. Okay, that is exactly why it is a 2 electron process. Okay, and always you will have another proton which will be released to the solvent. The other thing always now put this in your mind is whenever we have NAD plus NADH cofactor or coenzyme, okay, so the NAD plus NADH, this pair is always involved in the alcohol to ketone type, ketone, or I should say carbonyl. Could be aldehyde. So these are always going to be involved in catalyzing the alcohol to carbonyl and vice versa type of reaction. This is just put this in your memory. All the examples you're going to see in this semester, which uses NAD plus NADH as a coenzyme, always they're going to be doing alcohol to ketone, alcohol to aldehyde, or ketone to alcohol, or aldehyde to alcohol. These type of reactions. Yeah. Everybody with me?
Yeah.
Yes.
So this process, lactate to pyruvate, doesn't happen on its own, meaning that if you just give NAD plus, it will not happen. You need an enzyme as well. So it's an enzymatic process, and that enzyme is called lactate dehydrogenase. All right. So we're going to learn about enzyme classifications as we go along. So I want to point out that wherever you see dehydrogenase, okay, so the dehydrogenase enzymes are always going to be involved in redox reactions. Dehydrogenase, okay, always redox reactions, oxidation reduction reaction. This is what these enzymes do. They always do either oxidation or reduction, and always these are reversible. It can go this way or the other way depending on the need for the body. Right? Everybody with me? So just some of the things to remember is that NAD plus NADH is a 2-electron process. It's a hydride. Always it is involved, and it will be oxidation reduction process. And the enzyme that does this is going to be a dehydrogenase, and that dehydrogenase always does oxidation reduction process. Makes sense? But the enzyme cannot do on its own if it doesn't have NAD plus or NADH. Okay, so basically you need the enzyme to position the substrates. In our case, the substrate is lactate, okay, within the enzyme, and then the enzyme helps remove that proton, that H as a hydride, give it to NAD plus to make NADH. Make sense?
So it doesn't work in reverse, or it does?
It does, yeah. Yeah, this is a reversible process. So lactate dehydrogenase can also make pyruvate to lactate, depending on the need of the metabolic state. But if you do that, then you got to use NADH. Okay, got it? Everybody with me?
Yeah.
Okay, so now we also looked at another coenzyme, right? What was that? We have not looked at, we have talked about it. So the other one is FAD. Going to FADH2. Okay, so FAD can be either 1 electron or 2 electron. Okay, so from FAD you can go to FADH and then add another H to go to FADH2. So unlike the NAD plus NADH couple, which is always 2 electron as a hydride, okay, FAD could be either 1 or 2, but it doesn't work as a hydride. The mechanism is different. We will not be able to do the mechanism. It goes through a radical process, but just it is enough to know that the FAD-FADH2 couple, okay, is an H. It is an H acceptor or H donor. Okay, and not H minus. This is really critical to know. Not H minus. It is H. Okay. And this is reflected in the type of chemistry the FAD-FADH2 does. So FAD, FADH2 couple, the example we're going to see, okay, in the citric acid cycle, we're going to see only one specific example where whenever these guys are involved, they interconvert alkane to alkene. And this is, we're going to also see this in when you do the lipid chapter, fat metabolism. Okay, so still going from alkane to alkene is a 2-electron process. Okay, so going from alkane to alkene, we need, here this way we need FAD, and if you go the other way, we need FADH2. Still in a 2-electron process, but the type of reaction we're doing here is not alcohol to carbonyl, okay? Rather, it is alkane to alkene and vice versa. So this is another thing you got to put it in your memory, that the difference in reaction type between NAD plus NADH couple and FAD, FADH2 couple. Okay, so FAD, FADH2 is never going to do alcohol to ketone or vice versa. Okay, same is true for NAD plus NADH. It will never do alkane to alkene or vice versa. Yeah, so some general principles, could be exceptions, but these are the general principles that we need to keep in mind. Everybody with me? Have I lost anyone? Okay. The other thing to note, as I said, for the FAD is that it is not an H minus, it is an H. Okay, it could be 1 electron, but most of the time it is going to be 2-electron process. And it is so then it's going to be 2H, acceptor or donor, and not H minus. That is the main distinction here. Okay, everybody with me? All right. So the next thing we're going to talk about is something you have heard and done, I hope, some math in Gen Chem, and that is redox potential. So this is the next concept we're going to talk about. And redox potential is, it is designated as E. Okay, E is the redox potential, is the symbol of redox potential is E. So always, this is also another thing to remember, is the electrons they'll always going to flow from low to high redox potential. Okay, so if I give an electron to someone, okay, if I give an electron to Tanner, then Tanner must have higher redox potential than me. Okay, so to think about E as is like an affinity, so it's an electron affinity. Okay, it's an electron affinity. So higher E is equivalent to, so think about that as higher affinity for electron. Okay, so higher redox potential meaning higher affinity for electrons. So I am going to take the electron from someone who has a lower redox potential or lower affinity. Make sense? Do you see what I mean? So electrons always flow from low to high redox potential, and redox potential is, think about as an electron affinity. So higher E meaning higher affinity for electrons, right? So delta E, we have quite a few math for this concept. So delta E is going to be E acceptor, okay, minus E donor, right? And there's an equation, the delta G equation that relates to the delta E is by this equation is N F delta E. So N is the number of electrons involved in a redox process, and F is a Faraday constant, and the delta E is the difference in redox potential, okay? So that's the difference in redox potential. Now, N can never be a negative number, right? N always has to be a plus number as the number of electrons. Yes? Yeah, everybody with me? Because
Yes.
it's a number, it has to be a plus number always. Faraday constant is a constant, it is a positive number. So in order for delta G to be negative, what must the sign of delta E be?
Positive.
So delta E must be positive for spontaneous electron transfer. Okay? So for spontaneous electron transfer, delta E must be greater than 0. And it is, governed by this delta G equation, right? Delta G is negative NF delta E. So in order for delta G to be negative, delta E must be positive number. Got it? All right, so now let's look at one example here. The same lactate to pyruvate. So there are a couple of redox potentials I have in my hand. So we have pyruvate. So pyruvate to lactate is on its own 2 electron 2 proton going to lactate plus so this has a negative minus 185 millivolts, and then it is always coupled with the NAD pair. So NAD plus 2 electron plus H plus going to be NADH, right? We already read this above. So this is the same as H minus, right? So here, this is going to be negative 320. So between these two, which of these reaction pairs has a higher affinity for electrons?
NADH. I mean NAD plus to NADH.
So remember, higher affinity meaning higher E, right? So more positive number.
Pyruvate.
So that must be the first couple, right? Higher E meaning higher affinity for electrons. So the pyruvate couple is the one that has higher affinity. So then which couple is going to accept electrons and which couple is going to donate electrons?
Pyruvate would
will
accept.
NAD will take.
So pyruvate is going to accept, right? And which one is going to donate?
NAD. H.
NADH, not NAD plus, right? So that's the critical thing to notice. So here, the way I have written the reaction is the reverse of what we did above. Okay, here we did lactate to pyruvate, which was an oxidation process. But the way I have written the reaction here is going from pyruvate to lactate, which is a reduction process, right? Yes or no? Yeah?
Yes.
So because it is a reduction process, I must give NADH as my coenzyme and not NAD plus,
So you
right?
flip
Because
it.
NADH is the electron donor. So to make this reaction spontaneous, what will be the net delta E for the process? How do we do that? That's the question, right? So there are two ways to think about this. One is I know my delta E has to be positive, and that for that to happen, I can do equation 1 minus 2. Is that going to work?
Yes.
So if I do 1 minus 2, then so let's write the equation. Okay, so I do then as we did last class, do the left side of the equation, do the right side of the equation separately. Do not mix left and right. Okay, so pyruvate plus 2 electrons plus 2 protons, and if I do the subtraction, let's see what happens. And then we got minus 2 electrons, minus 1 proton, and then on my right side will be lactate minus NADH. And now the delta E is going to be what? Negative 185 minus 320, right? So basically it's going to be negative 185 plus 320. So plus 135 millivolts. So now if I rearrange, see this 2 electron cancel. I'll have 1 H left here, and my overall reaction now is going to be pyruvate plus, so NADH is going to come to the left side of the equation, plus NADH, plus 1 proton I'll have left, okay? And this is going to lactate plus NAD plus. And my delta is going to be plus 135 millivolt. So this is the net reaction that happened. Pyruvate is an oxidized compound. It is reduced by NADH. Okay, and there is a proton that was needed to make that alcohol part of the lactate, and that's how we make the lactate. And we make NAD plus. So because pyruvate to lactate is a reduction process, we must have NADH on the left side of the equation, right? So the delta E is going to be then, yeah, plus 135 millivolts. So that's why it is going to be a spontaneous process, right? So we can calculate delta G from this. ANF delta, what is the number of electrons? It is a 2 electron process, right? 2, N is 2. From this equation, if I plug it in the numbers, yeah. And Faraday's constant is, I believe, 96,000 something, 96485, I think. I'll give specific numbers. And it has unit, so the unit is going to be, so let's do 96.5. Kilojoule per volt times mole. Okay, and so that is the F. I also have delta E, which is 135 millivolt. So if I convert that to volt, I'll have 0.135 volt, right? So this volt will cancel, and this will be -2 times 96.5 times 0.135 kilojoule per mole. So that's my delta G for this process. Okay. Do you see everybody with me?
I have a
Yeah.
question.
Yeah.
The 2 electrons, you got that from the NADH?
The 2 electrons from, yeah, because this process, the pyruvate to lactate is a 2 electron process.
Okay, thank you.
I have another question.
Yeah.
How come you moved NADH and NAD plus to the opposite side when you
Yeah.
canceled?
Right, because NADH here is on the right side of the equation, right? So that's my kind of equation arrow, right?
Correct, yeah.
And look, this is minus, right?
Yep.
So if you bring it on the other side of the equation, that must be plus.
Gotcha. Yeah, no, that makes sense.
And then same thing here, NAD plus is minus here. When I bring it to the other side of the equation, that must be plus.
Sounds
Got it?
good. Got it.
And
You
so
also
the number of
mentioned-
electrons 2, that was just 2 electrons for the whole problem.
Yeah, this is a 2 electron process. I mean, the electrons are coming from basically the substrate, which is, so you go from pyruvate to lactate. What is happening chemically is what you got to think. And the source, so here going from if you do go from right to left, pyruvate to lactate, that's the net reaction. It's a 2 electron reduction of the substrate. And NADH is a coenzyme. It is not the substrate, it is a coenzyme, which is giving the H minus and a proton coming from solvent to the pyruvate to make lactate. Right? So we always consider the substrate. What is happening to the substrate? NADH, NAD plus is not a substrate, it is a coenzyme. Yeah?
Quick question.
Yeah.
Above you before you said that N could not be negative. Did you put the -2 just to signify that it was the electron?
Yeah, so 2 is the number of electrons, right?
Okay. So like if you figured up the delta G, would the G be around 26?
I don't know. You could do the math, find out what the number is. That what is coming out to be?
That's what it came out to be as.
Okay, so then it is -26 kilojoule per mole. Okay, so minus is already in this equation. So the delta G equation, I didn't change that. All I did is put the numbers in F delta E. Got it? So I said there's another way to do this, another way to think about it, okay? And I don't want to confuse you guys, but another way you can think of that is because it is a reduction of pyruvate to lactate, and I know I need NADH, what I could have done is that I could have rearranged that second equation to put NADH on the left. So I could have done this, pyruvate plus 2 electrons plus 2 protons going to lactate, and this is -185. So keep in mind, when you do this kind of math, you have to convert the millivolts to volts. That's the common mistake a lot of people do, because see that my FAD constant has volt, right? So if it is a millivolt delta E, you must convert to volt. Keep that in mind. Anyway, going back. So that's my first equation. Now, because pyruvate to lactate is a reduction process, and I know that, so I must have NADH. I could do that. I could bring NADH on the left. Okay, and then if I do that, then my right side is going to be NAD plus 2 electrons plus proton. But because I flipped the equation, I must flip the sign as well. Okay, so now it is going to be plus 320 millivolts. All right. So now I could simply add, instead of here we subtracted above, but we could simply add. So now if we do that, then pyruvate plus 2 electrons plus 2 protons plus NADH are going to be lactate plus NAD plus 2 electrons plus proton. And now my delta E is going to be simple addition, right? So it will be plus 135, same number. Okay, so now you see that 2 electron cancel on both sides, and then this proton is going to cancel. We're going to be left with 1 proton. So ultimately, we will end up with the same equation. Okay, lactate plus NAD plus, right? So this was our equation there. Then we have the same equation here. Right? Either way, you're going to go to the same conclusion, right? And that is that my delta E is going to be positive in both cases. So this process is going to be overall hexagonic and a spontaneous process. Make sense? So this is another way you can think about this type of problems. Got it?
Yeah.
So there is going to, so as I said, you should be able to see the worksheet that is on Blackboard. So practice solving the worksheet, and next class we're going to go through the worksheet, and I'm going to ask you guys to go through that math process and how to solve the math. Okay, so practice well ahead before class, and then so that we can move smoothly. Make sense?
Yes.
Yeah.
Yeah.
So we're not going to do any more material today because this is a lot of new things. So it will give you some food for thought. How to think about redox processes. Think about the oxidation reduction, how to calculate those, and some of the bottom lines we have learned about NAD plus NADH and FAD, FADH2. And things like that, okay? And then how to do the math. So these kind of problems already in the worksheet. So, this should help you to get started on that. So the quiz is supposed to open up at 12:04 or 12:05, I think 12:04. So you will have until 12:25, but then you'll have only 10 minutes to take the quiz, okay? So go ahead and go to Blackboard and then wait for the link to become active. And as I said, you must have your microphone and webcam active. It's going to go through the process, initial process.
I have a question.
Yeah.
Yeah. Okay. So when lactate goes to pyruvate and it releases a proton that goes with the solvent, does that cause a decrease in the pH of blood?
Yeah, so lactate, yeah, we'll talk about lactate, how is lactate produced and what happens to it. Yes, so lactate does reduce the pH of the blood. That's why the muscle becomes acidic. Yeah, so we'll talk about that sometime during class.
Okay, thank you.